Okay, so I wanted to make a video here, as was suggested to me, to cover the Chapter 11 stuff since so many people are missing class and whatnot. We kind of skipped over 11.1. You can go ahead and pause it here and make sure to get the big idea stuff. We're doing significant tests now, so menu, statistics, stat tests, and we're either going to do a t-test or a two-sample t-test. So we're starting here with the regular old t-test where we're talking about mu and x bar. Remember, x bar is our sample mean. Mu is our population mean. So we're trying to test on that. So we have null hypothesis where mu equals some null value, and our alternatives are mu is less than the null value or mu is greater than the null value. Those are the one-sided. Mu is not equal to the null value. That's the two-sided. Here's our interprets. Hopefully they look a little bit familiar. Assuming the null is true, mu equals whatever. There is a p-value probability of getting an x bar of blank or more extreme purely by chance. Because p-value is less than alpha, we reject the null and we do have convincing evidence for the alternate. Or because the p-value is greater than alpha, we fail to reject the null and we do not have convincing evidence for the alternate. Okay, so let's skip on and learn how to do it in the calculator and do it in the 4 C's. So we're skipping over this real quick. Okay. So instead of making everybody take their temperature, we're just going to use this data. It says, for many years, doctors have told people that a normal body temperature is 98.6 degrees Fahrenheit. Today, we'll find out if that's true. Record your body temperature at the front of the room. Think of the class as a simple random sample of all high school students and use applets to find this stats thing to find it. Well, we're just going to use this data. Our x bar is 98.237. Our S, our standard deviation of the sample, is 0.822. And N is 32. So our procedure is now no longer going to be a one prop Z test. It's going to be a one sample T test for mu. Mu is going to be, in this case, the true mean body temperature for high school students. And so our hypothesis, our starting is going to be that it's 98.6, but our alternate is going to be that it's not 98.6. So the null hypothesis is mu is 98.6, and the alternative hypothesis is mu is not 98.6. We're told to use a 5% significance level. Our statistic is that 98.237. Our evidence for the alternate is just that 98.237 is not 98.6. The conditions don't change. We have a simple random sample, so we can generalize the population. 10%, 32 is less than 10% of all high school students, so we can do it without replacement. And we have more than 30, so our sampling distribution is approximately normal. Our general formula has always been statistic minus parameter over standard error. Now remember that used to be, for us it was, p hat minus p over square root p times 1 minus p over n. That was for proportions. Well, now we have to do it with means. So our statistic is x bar. Our parameter is mu. Our standard error isn't the p times 1 minus p over n. Now our standard error is just s over the square root of n. So our specific formula, t, not z, is going to be x bar minus mu over s divided by the square root of n. So we plug in our numbers, and we can do this all in the calculator. Matter of fact, we should have done this kind of right from the get-go when we have our hypotheses. But I'll show you how to do it in the calculator here. Bring it on screen here. So you do menu, statistics, and we're going to do stat tests, and we're going to do just a straight-up t-test. Change this to stats. Our null is that it's 98.6. We got 98.237 with a standard deviation of 0.822 with a sample of size 32. and we're keeping it not equal to. Remember, you can change it to greater than, less than, but in this case it said different. So we leave it as that, hit OK. There is our t value that we just found. There's our p value we're going to need. We've got all the information we need right there. So we get a t of negative about 2.5, which is our test statistic. Pictures there to kind of illustrate the point. And the p-value came out to be 0.018. So our conclusion, which you have the Mad Libs for from the notes you just took, is assuming the null is true, is always the start. There's a 0.018 probability of getting an X bar. They use this, 98.237 or 98.963. So the idea is from 98.6 down to 98.237 is some 0.4 something, right? 0.3 something. So they just added it to get to the other extreme. You can say something like to get probability of getting an X bar as far away from 98.6 as 98.237 or more purely by chance. Something to that effect. You're showing that you understand this is a two-sided test. So because this number is so small, because our p-value is so small, we're kind of ruling out purely by chance as a thing. So 98.6 just probably isn't true. Because 0.018 is less than 0.05, we reject the null, and we do have convincing evidence that the mean body temperature is different than the doctor's claim. So if we were to construct a 95% confidence interval, would the interval contain 98.6? Well, no. Like, this is the 95% is kind of the equivalent of the 5%. If you create an interval, a 95% interval, and I think we did this, it went from like 96 point something to 98.4 or something like that. That should be a 9. Well, because it's outside of this, like 5% is outside of this, that would be like your p-value range of that our significance level. If alpha is 0.05, well, that's outside of this range. 95% is within it, so 5% is outside of it, essentially. So our p-value, when it's outside of the range, is going to be less than whatever's left over from here. So no, the significance test rejected it, so it is not plausible value contained in the interval. Pretty simple as that. It's the idea of connecting the confidence intervals to the significance test here. Okay, let's get the big ideas here. We choose, check, calculate, conclude. This is kind of our making connections. You can pause it here and write all this down. And then we'll move on to 11.3 and 11.4 and 11.5. Okay, so now we're moving on to difference of means. We're going to have a two-sample. Get all this written down here. We have our conditions again. Here's our different hypotheses. We want to know our null hypothesis is always going to be mu1 and mu2 are equal. So mu1 minus mu2 would be 0. Less than means mu1 is less than mu2 would mean the difference is less than 0. Greater than would mean mu1 is greater than mu2. There'd be greater than 0 in a difference. And if the difference is just not 0, then mu1 is not equal to mu2. I like these because this is what you actually see in your calculator when you do this. So I think it's a good idea to use these. But do define mu1 and mu2 with direction. It is like the difference in mean whatever, this minus this. That's what you're going to say. Now here we're moving away, and this has always been the case, we just haven't talked about it very much. Independent random samples or random assignment. Like independent random samples let us talk about generalize to a population. Random assignment allows us to talk about causation. Both are good things. It's lovely to have both, but you're really not going to be able to. If you have random assignment, you can talk about causation, but you can't talk about anybody beyond the group you experimented on. Whereas random samples will let you talk about everybody, but probably don't let you actually talk about causation, only correlation. 10% in condition, you only have to check when you're sampling without replacement. And usually if you're just given, hey, here's a volunteer group, that means you can do it without replacement. You don't have to worry about the 10% condition because you're not trying to generalize to a larger population anyway. The same 3 ways to get normal. If you don't have a sample size of 30, you can look at and see if both populations were normal or if the sample data shows no stronger outliers on either distribution. Okay, same thing. Let's move on to how to do this. Make sure to pause this if you need to get all the stuff down here to get it all. And we'll go on to doing this in the calculator and drawing our conclusion, doing the 4 C's. Okay, researchers from Harvard and Columbia University wanted to know if taking a multivitamin improves memory. To investigate, they took 3,562 volunteers and randomly assigned. So we can't talk about everybody, and so we're not going to need the 10% condition again. Because we're assuming without, they're not assuming, but we can do it without with replacement. Randomly assigned half of them to take the multivitamin, half to take a placebo. Here are the summary statistics for the scores and memory tests the subjects were given at the end of the year. So random assignment, that gives us, we can talk about causation. We have our 2 different things here. This is going to allow us, both of these are way greater than 30, so we have the central limit theorem, so our conditions are all met. Is there convincing statistical evidence that multivitamins cause and improve memory? So like this one greater than this one, multivitamin greater than placebo group. So now our procedure, because we have 2 samples, is in fact going to be a 2-sample test. This 2-sample, they forgot the T, for mu1 minus mu2. The parameter is the true difference of mean memory test scores in multivitamin minus placebo. You must define the parameter. Our hypotheses are going to be they're equal, is the null hypothesis, and our alternate hypothesis is going to be mu1 is greater than mu2. Significant levels, 0.05. Our statistic, we need to do 62.4 minus 61, and we're going to get 1.4. So we got a positive 1.4 difference, and that is our evidence that the multivitamin group was 1.4 points better than the placebo group. Our conditions we just talked about, random is fine. We can show causation. The central limit theorem applies to both of them. So we've got a normal distribution. Okay, let's put it all into the, matter of fact, right now we can put everything into the calculator. We don't even need to start writing anything down yet. So, menu, statistics, stat tests, we're going to do 2-sample t-test. Stats. X bar 1 was 62.4 and 18.4 with a sample size of 1781. X bar 2 was 61, 18.7, also 1781. And we were saying mu1 greater than mu2, and pooled we don't mess with. Hit OK. Here's our T and here is our P. The 2 numbers, we're going to get this in a second. We might as well have them. We've got a really small p-value. If we did a 2-sided, this number would be twice the size. So that's where if you accidentally did not equal to, you'd get a double there, double that value there. But we did it as a 1-sided, so because that's what we were asked for. Okay. General formula is this. Well, we were using X bar, matter of fact, let's talk about it. Stat minus parameter over SE, standard error. Well, the stat now is not X bar, it's X bar 1 minus X bar 2. Our parameter is mu1 minus mu2. And our standard error is a lot more convoluted than it was before. We have 2 standard deviations, standard errors. So we have S bar S1 squared over N1 and S2 squared over N2. Now mu1 minus mu2, because we're assuming they're the same, that's our null hypothesis. That's just going to be this value is going to be 0, so we can end up just not using it. But we plug our numbers in. We already have the t from the calculator. You're just showing your work. If you didn't write the -0, you don't have to. Don't worry about it. There's the picture version of it. Our test is with 2.25, and the p-value was 0.0123. So again, in conclusion, we're assuming the null is true. There's a p-value probability of getting a difference of 1.4 or greater purely by chance. And because 0.0123 is less than 0.05, we reject the null, and we do have convincing evidence that multivitamins improve memory. And it should be noted, improved memory for this group. We can't talk about that with anybody else if we did not randomly sample our 3,652 people. So based on your conclusion from the significance test, which of the two errors, type 1 or type 2, could have been made? Interpret the consequence of the error in context. So type 1 error is when we reject the null when we shouldn't. Type 2 error is we fail to reject the null when we should have. So we rejected the null so we could only make a type 1 error. We decided multivitamins improve memory, but they actually do not. People are wasting money buying multivitamins would be the consequence. Just understand we didn't necessarily make a type 1 error, but a type 1 error is the only error we could have made here because we rejected the null. Okay, so now let's move on. That was the difference in means. And, pause this, do whatever you need to do, obviously, to catch up. Maybe even, do the homework on this one. Then you can come back and do the next video in a second. Or if you just want to get the notes down, we'll move on. Oh, sorry. Nope, we need the big ideas here. So pause it here, get the big ideas down, and we'll move on to the 11.5. Okay, climate change again. Suppose that 32 weather stations were randomly selected across the globe. For each station, the peak annual temperature between 1900 and 1940 was found, and the peak annual temperature between 1960 and 2000 was found. The differences were calculated for each station, later temperature minus earlier temperature. The mean of the differences was x bar diff equals 0.35 Celsius, and the standard deviation was S diff of 0.296 Celsius. Is there convincing statistical evidence that the peak global temperatures increased? So let's just think about that. On average, from 1900 to the 1900s. We do have the random selection, and 32 greater than or equal to 30, and 32 is going to be less than 10% of all weather stations. I think we had something like 1900 or something when we did this a couple weeks ago, or a few days ago it may have been. So this one we've only got, just notice, like you say, is this a one prop or two prop, or I'm sorry, one prop, one sample or two sample? Well, we only have one X bar. So we've got to do a one sample. In this case, it's a matched pairs. You're comparing one weather station to itself from the later part of the century to the earlier part of the century, and then taking another one and taking that difference and averaging it with the difference on the next one, and averaging it with the difference on the next one, and on and on and on. So mu diff is the true mean difference of peak temperatures from late to the early 1900s. And hypothesis is there is no difference, or is the null hypothesis, or the alternate is the difference is greater than 0. It's gone up. Significance level is 0.05. Our statistic is our x diff of 0.35. Our evidence is that 0.35 is greater than 0. Again, you don't have to put the evidence on the actual test or anything like that. It's just illustrating the point here. Conditions, we've got them all. We have a random sample of 32 stations, so we can generalize to all stations. 32 is less than 10% of all stations, so we can sample without replacement. And we satisfy the central limit theorem, so the sampling distribution is approximately normal. Okay, matter of fact, this is the time again. Let's just throw everything into the calculator. So we're doing menu, statistics, stat test, and we're doing back to the t-test because we only have one sample. Change to stats, and we have an x diff our mu is 0. Our x bar was 0.35. Our Sx was 0.296. And we had 32 stations. And we are saying greater than. Mu is greater than the null value. So we get a t of 6.69, and we get, hopefully you understand that this is a decimal, 7 zeros, and a 9. That's all but basically 0. So we have an incredibly small p-value. We are almost 7 standard deviations away from the mean, the assumed mean. Okay. So our general formula, now the specific formula is the one we did before, because we only have one sample, so we go back to the one sample. You just use the little diffs to illustrate the point. So we plug in our numbers, and we get t is 6.69. We can't even draw this small enough over here. They said that it's basically 0. Just to illustrate the point, it's basically 0.1, 2, 3, 4, 5, 6, 7, 9. That's our p-value. It's obviously way less than any, alpha we could even think of or to use. So, assuming the null is true, that there is no difference, there is a 0, and let's just be pedantic here, 0, 2, 3, 4, 5, 6, 7, probability of getting an x diff of 0.35 or greater purely by chance. So there's no chance that it was just random chance of getting that. Because it's less than 0.05, we reject the null and have convincing evidence that the peak temperatures increased over the course of the 1900s. Okay, there's your big ideas. The difference between one sample and two sample. Go ahead, pause this here, get all this stuff written down, and then jump yourself into the homework. There you go. Good luck.